welcome to True Projects. In this video, we are going to explain about the project entitled as Enhancing Text Classification Through Quantum Transfer Learning, a hybrid quantum classical approach with complex kernel self-attenuation networks. So before getting into the video, let me give you the brief description about the project. The title represents a hybrid approach that improves text classification by combining quantum computing concepts with classical deep learning. It emphasizes the use of quantum transfer learning and complex kernel self attenuation to achieve more accurate and effective text understanding. Coming to the abstract, in recent years, artificial intelligence has become widely used in applications such as text classification, image recognition, and financial prediction. Although classical AI models perform well, they still faces challenges when dealing with complex and high dimensional data. To overcome these limitations, this work introduced a hybrid approach that combines quantum computing concepts with deep learning. The proposed model, called the Complex Quantum Kernel Self Attenuation Network or CQKSAN, integrates quantum circuits, classical neural networks, and self attenuation mechanism. By using birth embedings and quantum transfer learning, the model achieves better feature representation. Experimental results shows that CQKSAN performs better than existing models like LSTM, BERT, and Robot A, proving that quantum enhanced learning can significantly improve text classification performance. Coming to the existing system, traditional text classification systems mainly depends on classical deep learning models such as LSTM, BERT, and Robot A. These models analyze text by converting words into numerical values and learning patterns from sequential or attenuation based structures. While they provide good accuracy, their performance is limited by classical computing capabilities. They may also struggle with highly complex text features and large data set. In addition, using accuracy alone does not allow reflect true model performance, especially when the data is imbalanced. Training these models on multiple datasets also requires high computational cost and longer execution time. Coming to the proposed system or base paper work, the proposed system introduced CQKSAN, a hybrid quantum classical text classification model. In this approach, the input text is first converted into numerical vectors using a pre-trained birth model. These vectors are then processed through a hybrid architecture that combines classical neural networks, quantum computing layers, and a self-attenuation mechanism. Quantum computing principles such as superposition and entanglement helps generate more informative and optimized features. The self-attenuation layers allows the model to focus on the most important words in the text. This combination results in improved learning and higher classification accuracy compared to traditional models. Coming to the dataset, the movie reviews dataset with sentiment labels is used to evaluate the performance of the proposed model. This dataset contains a large number of movie reviews collected from real users, where each review is labeled as either positive or negative. It is commonly used for sentiment analysis tasks and provides realistic text data for training and testing models. The dataset is well structured, making it easy to pre-process and apply advanced models such as birth and hybrid quantum based architectures like CQKSAN. Coming to the novelty or extension or enhancement or improvement. To further improve the performance of the proposed CQKSAN model, an extension is introduced using a bidirectional gated recurrent unit or BiGRU. BiGRU process text sequence in both forward and backward directions, allowing the model to understand the fully context of the sentence. This helps capture relationship between words more effectively. When BiGRU is integrated with CQK-SAN, the model gains stronger temporal and contextual understanding, leading to improved feature extraction and better classification results, especially for complex text data. Along with that, as an extension, A Flask framework is used to develop a user friendly interface that allows users to provide input data for prediction. The inputs are pre processed and passed to the trained model based on the data set. The predicted results are then displayed through the web interface, making the system easy to access and usage. Coming to the flow of the work, first, library initialization and environment setup. The workflow begins with the initialization of the programming environment by importing all required Python libraries. Warning messages are suppressed to ensure clean and uninterrupted execution. Core libraries such as NumPy and Pandas are used for numerical, computational, and data handling, while scikit-learn provides evaluation metrics including accuracy and Matthews correlation coefficient. TensorFlow and Keras are employed for building and training deep learning models. Sentence Transformer is used to generating birth-based embeddings, and Matplotlib and Seaborn support data visualization. Next, birth model initialization for text embedding. In this step, a pre-trained birth model, specially birth-based mean tokens, is loaded using the sentence transformer framework. This model transforms raw textual movie reviews into dense numerical vectors that captures both semantic meaning and contextual relationships. This embedding serves as a standardized input features for all subsequent classification models, enabling consistent and meaningful comparison. Next, dataset loading and exploration. The movie review dataset is loaded from a CSV file for experimentation. Initial exploratory analysis is performed to understand the structures of the data, including viewing samples records and examining class labels. The distribution of positive and negative reviews is analyzed and visualized to identify potential class imbalance, which is crucial for selecting appropriate evaluation metrics such as MCC. Next, data pre-processing. Text pre-processing is carried out to prepare the data for modeling. The movie review texts are converted into numerical representations using the previously initialized birth model. After embedding generation, the dataset is divided into training and testing subsets. The splits ensures unbiased performance evaluation and helps access the generalization capability of the models. Next, baseline model LSTM implementation. A long short term memory network is implemented as a baseline text classification model. The LSTM is trained using the birth embeddings to learn sequential patterns within the data. Once trained, the model performance is evaluated using accuracy and Matthews correlation coefficient, and the results are stored to enable direct comparison with more advanced models. Next, proposed model. The proposed complex quantum kernel self attenuation network is developed as a hybrid model combining classical neural networks, quantum kernel based feature processing, and a self attenuation mechanism. The quantum component leverages quantum computing principles to enhance feature representation, while self attenuation allows the models to focus on the most informative parts of the text. The CQK SAN model is trained using the same birth embeddings and evaluated using accuracy and MCC to ensure fair comparison with the baseline model. Next, extinction model. To further enhance performance, an extended version of the CQK SAN models is implemented by integrating a bidirectional gated recurrent unit layer. The bidirectional GRU process input sequence in both forward and backward directions, capturing richer contextual dependencies. This extension improves temporal feature learning and is trained to evaluate in the same manner as the previous models. Next, performance evaluation. The performance of all implemented models with BiGRU is systematically compared. Evaluation is carried out using accuracy to measure overall correctness and Matthews correlation coefficient to provide a balanced assessment, particularly for imbalanced data set. All results are compiled into a structured data frame for detailed analysis. Next, result visualization and analysis. Graphical visualizations are created to compare the performance of different models. Bar charts are plotted for both accuracy MCC, enabling clear and intuitive comparison. These visual results highlights the effectiveness of the proposed CQK SAN model and demonstrate further improvement achieved through the BiGRU extension. Coming to the front end, the front-end workflow begins with the initialization of web-based user interface developed using the Flask framework. The user enters textual data such as movie reviews into the input form providing on a web interface. Flask routes are defined to handle incoming requests from the front end. The main route renders the home page containing the input form, while a deactivated prediction route process user submitted text. Before passing the user input to the trained model, basic validation is performed to ensure that the text field is not empty and does not contain invalid data. The validated user input is converted into numerical form using the pre-trained BERT model. The generated embeddings are passed to the trained classification model such as LSTM, CQK-SAN or CQK-SAN with ByGRU. The raw prediction output from the model is post-preprocessed to generate a user-friendly result. This indicates mapping numerical class labels to meaningful textual descriptions such as positive or negative and optionally computing confidence scores to enhance results interpretability. The process prediction result is sent back to the front end and dynamically rendered on the web page. The front end allows users to submit multiple inputs without restarting the application. Finally, the Flask application is configured for development on the local server or platform. This ensures accessibility through a web browser, allowing users to interacting with the quantum enhanced text classification system in a user-friendly and scalable environment. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consisting of application framework is Python 3.7.2, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. And these are the model files which contain algorithm information which will be loaded into the project code during the runtime. IPYNB file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project, firstly, you need to copy the path of the code folder from the address bar of the file explorer. Then open command prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py in the command prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the Flask framework and paste it into any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front end using Flask framework. In this page, we have home button and sign up button. Firstly, click on sign up button so that the create account will be opened where we need to enter the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on sign up so that all the given details are stored in signup.db and login.html will be opened where you need to access the application by entering username and a password. Then click on login so that the prediction page has been displayed. In this page, we have prediction button, graphs button, notebook button, and sign out button. Firstly, click on prediction button so that the text classification prediction form will be displayed where you need to enter the text and click on predict. So firstly, let us enter the text and click on predict so that the given input is pre-processed and the output is displayed as a positive text. The confidence level is 99.53%. We also have the probability distribution like positive is 99.53%, negative is 0.47%. What is the input text we have given? We can check it here. We have 430 words along with 2196 characters. We have the model information like model type, encoder, architecture, and classification. We also have the recommendations and insights like sentiment analysis, action required, usage recommendation, quality assessment, and next steps. Here we have try another text or view analytics. By clicking on try another text, we can give the other text. We have entered the text and click on predict so that the input is pre-processed and the output is predicted as negative text. The confidence level is 99.64%. We also have the probability distribution like positive percentage is 0.36% and negative is 99.64%. What is the input text we have given? We can check it here. And we also have the model information like model type, encoder, architecture, classification. We also have the recommendation insights like sentiment analysis, action required, content review, risk assessment, quality improvement, follow up actions. Now, click on graphs so that the graphical representation of the projects will be displayed. And let us check one by one. First, we have movie reviews class distribution graph. The graph shows the distribution of sentiment classes in the movie review data set. It indicates that both positive and negative classes contain an equal number of reviews with 1,000 samples each. This balanced dataset ensures unbiased model training and reliable evaluation of classification performance. Next, we have confusion matrix graph. The confusion matrix shows the classification performance of extended CQK-SAN and BiGRU model. Out of all samples, 185 positive and 200 negative reviews are correctly classified, while only 5 instances from each class are misclassified. This indicates a very high prediction accuracy and balanced performance across both sentiment classes. Next, we have algorithm accuracy comparison graph. The graph compares the accuracy of three different models used for text classification. The baseline LSTM model achieves an accuracy of 76%, while the proposed CQK-SAN model significantly improves performance to 96%. The extended CQK-SAN with BiGRU achieves the highest accuracy of 97%, demonstrating the effectiveness of quantum integration and bidirectional temporal learning. And next we have algorithm MCC comparison graph. The bar chart compares the MCC scores of three algorithms. MCC stands for Matthews Correlation Coefficient. LSTM, the proposed CQK-SAN and its extension CQK-SAN plus BiGRU. LSTM has the lowest performance with an MCC of 0.53%, while CQK-SAN significantly improves performance to 0.93%. The extension with BiGRU achieves the highest MCC of 0.95%, indicating the best predictive capability among the three. Then click on sign out. So finally, the integrating quantum transfer learning with complex kernel self-attenuation works improves text classification performance. The hybrid approach captures intricate patterns and semantic relationship better than classical models. These results highlights the promise of quantum classical methods for advanced NLP tasks. This is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.